Okay, we actually did some study of molecular motion in physics 1b, thermal physics. We know there are three types of motions when it comes to a molecule. There's translational motion, rotational motion, and vibrational motion. So here's a molecule. It can be made of several atoms, and this molecule can move from place to place, so the center of mass of that molecule can move. Okay, this is called translational motion. And then on top of that, the molecule can also rotate. Here's the axis of rotation, can rotate. That's rotation. And thirdly, within the molecule itself, you have different atoms. These atoms can oscillate back and forth. That is called vibration. So these are the three types of motion, three modes of motion associated with a molecule. And each of them has energy, and the energy of each of them is quantized to some extent. So let's take a look. First of all, let's look at the translational motion. The translational motion, basically, we put a gas in a box. The gas emits a whole bunch of molecules. So let's look at the translational kinetic energy of each of these molecules. This is essentially a three-dimensional infinite well, right? Particle in a box. And we know how to calculate the energy levels of particle in a box. You remember from the third chapter, chapter 41, right? We got infinite square well, where the 1D or 3D doesn't make that much of a difference. The energy goes like 8 squared over ml squared times n squared. I mean, there's a pi, there's an 8 here, but I don't really care that much. And there's a quantum number n squared, infinite square well. What I'm interested is, I want to estimate the degree of quantization, that is, between one quantum level and the next quantum level. What is the energy gap, delta E? Let's see that. First of all, when n is very large, okay, then the difference between the adjacent energy levels, which we call delta En, this is between n and n plus 1, we call delta En. It's a very small fraction of En itself. You can see that? This is the expression for En, right? Delta En is when you go from n plus 1 back to n. So here, the beginning is n plus 1, the end is n. So it's n plus 1, the whole thing squared, then minus n squared. If you did that difference, you get 2n. Okay? 2n plus 1, actually. And you divide it by n squared, so overall the ratio goes like 1 over n. If n is a very, very large number, then you can just forget it. The energy gap is a whole lot less than the energy itself. Therefore, the energy quantization is negligibly small. Now, what is the value, roughly the value of delta En? Well, we take E of n plus 1 minus En. Let's forget about the n squared thing for now. Let's just look at for very low values of n. So you only have h squared over ml squared. Okay? To estimate its order of magnitude, let's use the same old trick. Multiply numerator, denominator by c squared. So you get hc squared times mc squared and l squared. We have only done this with electrons in a very small box before. Now it's a very different story. We have a molecule in a very large box. Okay, first of all, the molecule is much more massive than the electron. Even the smallest molecule we can talk about, the H2. Okay, H2, that's twice the mass of a hydrogen atom. The mass of each hydrogen atom is roughly the mass of a proton, and the mass of the proton is nearly 2,000 times the mass of the electron. Okay, the mass of electron, mc squared, is about half of MeV. MeV is a million electron volts. You time that 2,000, what do you get? You get about 1,000 MeV, right? Or 1 GeV. Actually, it's more like 931, but who cares? It's pretty close to 1,000 MeV, which means 10 to the 9 eV, or 10 to the 3 MeV. That is the mass of one hydrogen atom. The molecules actually would be even more massive than that. And worse yet, this L here is not 1 nanometer. It's not even close to that small. It is about order of magnitude is a meter. We're talking about, a gas molecule in this room, right? We're not talking about confining the molecule in very, very small space. So this, you have a very large denominator in both mc squared and L. The result is an incredibly small value of 10 to the negative 21 eV. That's the energy gap. Energy gap. On the other hand, when you put a whole bunch of gas molecules in this room, how much kinetic energy of translation does each one have, roughly? That depends on the temperature, right? We learned that in physics 1b, that at T equal to 300 Kelvin, the typical energy is kT. K is the Boltzmann constant, and that when T equals 300 Kelvin, K times T is roughly 1 over 40th of an EV. 1 over 40th EV. How does that compare with 10 to the negative 1 EV? Incredibly different. So n is very large because this side, this thing here is only 10 to the negative 1 EV. You have to multiply this by a huge n value to get 1 over 40th of an EV. N being so large, the energy gap is a tiny, tiny fraction of the energy itself, and therefore, what is our conclusion? Yes, indeed, energy, the kinetic energy of translation motion of these molecules in this room is quantized in principle, but the quantization is negligibly small because the energy gap is a tiny, tiny, tiny fraction of the total translational kinetic energy. So we can effectively say, let's forget about the quantization of energy for the translational motion of the air molecules in this box, which is our room, and we can say it's continuous. Now, more interesting things happen when you go to the second mode of motion, that is the rotational motion. So here you have a diatomic molecule. One has a mass m1, that's one atom. The other atom has a mass m2. They're separated by distance r. So you can study its rotational motion. The rotational motion, as we learned from physics 1a, the kinetic energy of rotation is 1/2 I omega squared. I is the rotational inertia, which can be, for diatomic atom, can be written as mu r squared. Mu is the reduced mass, m1, m2 over m plus m2. We're measuring about the center of mass. Okay, we measure I about this is ICM, and r is the separation between these two atoms in the molecule. So that's the rotational inertia. And how do we quantize this quantity? This is the classical expression. In quantum mechanics, there is a very simple and clever way to quantize this energy with very little effort. And that is, let's rewrite this as L squared over 2I. L, as you know, is I omega. That is the rotational angular momentum, right? We saw that in chapter 12, actually chapter 11 of physics 1a. This is old stuff. We already know that. We write it as L squared of 2I, not as I omega 1/2 I omega squared. The reason we want to do that is because L is an angular momentum. Any angular momentum, rotational, translation, orbital motion, spin, whatever, any angular momentum is always quantized in quantum mechanics, and it's always quantized in the same exact way. That is, if you tell me the quantum number associated with that angular momentum, I can tell you immediately what is the total angular momentum equal to, the magnitude. Also, what are the possible values of its projection onto the z-axis. Okay, in this case, for the rotational angular momentum of the molecule, we do not use the letter L for the quantum number because that confuses with the letter L we used for orbital angular momentum for the electrons. This is rotational angular momentum for the entire molecule. Okay, so we use a different letter J. We call it J. Okay, if this is the quantum number associated with the rotational angular momentum, then clearly, due to the general rule of any angular momentum in quantum mechanics, L squared, the magnitude squared of the rotational angular momentum, must be equal to J times J plus 1 times h bar squared. It's always like that. And J is a number, is a quantum number 0, 1, 2, 3, and so on. And therefore, after we write it L squared over 2J, L squared over 2I, I can rewrite L squared as J times J plus 1 h bar squared. This is how I quantize the rotational energy. Okay, very easy to do. And let's do some order of magnitude estimation. E-rotation, with the order of magnitude estimation, J turns out to be not a very large number. Okay, unlike that N in the translational case, J is, order of magnitude 1, and therefore the order of magnitude is just h bar over 2I. And again, multiply everything, numerator denominated by c squared, so this h bar c, the whole thing squared, and mc squared and r squared. H bar c is 197 eV nanometer, approximately 200 eV nanometer squared. Mc squared, again, we have to use the mass of the molecule, even the smallest molecule, which is H2. We're talking about 10 to the 9 eV, okay, 10 to the 9 eV. And then the separation, however, we're talking about separation between two molecules. or two atoms in the same molecule, that's typically of the order of a fraction of a nanometer. So we use 0.1 nanometer as estimation, and that will give us 10 to the negative 3 eV. Okay, 10 to the negative 3 eV, otherwise known as 1 milli eV. 1 milli eV. Now, how do I know that this J typically is not a very large number? At room temperature, for a tank of gas room temperature, the rotational kinetic energy for the gas molecules, typically J is not a very large number. It's because due to the equipartition of energy, the translational energy, rotational energy, they roughly have the same order of magnitude because the collision between molecules will randomly redistribute the kinetic energy from the translational mode to the rotational mode and back and forth. And whether it's translational or rotational energy, the average energy per molecule, translational or rotational, has the same order of magnitude, about kT. Right? And when T equals 300 Kelvin, kT is 1/40th of an eV. Okay, it's about 0.024 eV, to be more exact. And that actually is not that different from the rotational energy of this from this expression, even without considering J. So if you do not consider the J, this part alone will give you roughly the same order of magnitude. I mean 10 to the negative 3. So therefore, J does not have to be a very large number to make E rotational close to close to kT. So J is typically just a single digit, like 1, 2, 3, or so on, not very large. And we can now find the energy spectrum, energy diagram. We're going to plot an energy diagram for the rotational, translational, kinetic energy of a typical molecule. Okay, you know the energy of the rotation is quantized. 0, 1, 2, 3, 4. Here's J equal to 0, no rotational energy at all. 1, 2, 3, 4, and so on. The energy gap between adjacent rotational energy levels is also the energy of the photon if the photon decides, if the system de-excites from one level to its immediate neighbor downstairs. A photon is emitted like this, and the energy of the photon is the difference in energy between this level and that level. Let's see what is the frequency and what is the energy of that resulting photon. Let's see here. E photon equals delta E rotational, so you go from here to there. Okay, adjacent, so you go from J down to J minus 1. And this is the expression for J, Ej, this is the expression for Ej minus 1. And then you see here, what you get is a constant times J. J. And here J equals 1, 2, 3, 4, 5, and so on. And you can see the energy gap is not uniform. The energy gap actually grows linearly as J increases. So here you have here's one gap, here's twice as much, 3 times as much, 4 times as much, 5 times, and so on. Okay. Now, we know that this expression, h bar squared over I, or over 2i, is roughly 10 to the negative 3 eV. Okay? And this J is like, usually a single digit number, 1, 2, 3, 4, 5, and so on. And therefore, the overall order of magnitude of E photon is about 10 to the negative 3 eV. And that puts it in the microwave range. Okay? The frequency corresponding to this much energy of a photon is about 10 to the 11 hertz. That makes sense, because for visible light, we're looking at 10 to the 14 hertz, 3 orders of magnitude higher in frequency, and the energy is also 3 orders of magnitude higher. Instead of 10 to the negative 3 eV, we're talking about 1 eV. Okay, actually it's between 1.6 and 3.2 eV, but the order of magnitude is 1 eV. So when you compare with visible light, for the rotational energy of a typical molecule, the energy of the photon is 3 orders of magnitude lower, and so is the frequency of that photon. This frequency, 3 orders of magnitude lower than visible light, is in a microwave range. And you can see here, the quantization is a prominent feature of the energy spectrum. The energy gap is comparable with the energy itself. You cannot ignore the energy quantization. These are not continuous at all. Delta E rotation over E rotation itself, you know what delta E rotation is right here, divided by E rotation itself, which is, like J plus whatever. And the answer you get is roughly equal to 1, because 2 over J plus 1, J is of the order of unity, and therefore, there is a lot of quantization going on here. You cannot ignore that. The quantization is prominent. Finally, let's take a look at the third mode of motion within the for the molecule, which is the vibrational motion within the molecule itself. Vibrational motion. All right, I have a plot here for a diatomic molecule. I have a plot of the potential energy of the diatomic molecule as a function of R. R being the separation between these two constituent atoms of the molecule. And clearly, the energy is the lowest at that particular separation R naught. This is where you're going to likely find the distance between the two atoms. But here's one atom, here's another atom. It doesn't mean the atoms will always be this far from each other at R naught. They can actually do this. They can breathe like this. Okay, so they go further away, closer, further away, closer. How far can they go? They can go this way, they can go that way, depending on how much energy the system has. If the system has only this much energy, it's stuck here. Okay, it cannot vibrate at all. If it's got a slightly higher amount of energy, then it can go between this R and that R, between R minimum and R maximum. It can oscillate back and forth, back and forth. If the energy is not that high compared with this minimum value, then the range of the motion is quite small. We only need to look at the bottom part of this curve. This curve is complicated, but the bottom part of this curve resembles a simple harmonic potential of R minus R naught squared. So you go a little bit, tiny bit away from R naught, either this way or that way, you're going to encounter parabolic potential. And the parabolic potential, of course, leads to simple harmonic oscillation. So we can approximate the vibration as a simple harmonic oscillation. And for simple harmonic oscillation, we know how to find the associated quantized energy. We learned that. We spent quite a bit of time studying that, the so-called quantum oscillator, in chapter 41. Remember that? Okay. This is the resulting vibrational energy level diagram. You see here, the energy associated with vibration is equal to, I should bring this back, is equal to a quantum number plus 1/2 times hf, and this quantum number is 0, 1, 2, 3. Here I do not use the letter n, I use the letter v, v standing for vibration. So that v is actually a quantum number here, 1, 2, 3, 4, and so on. You remember that from chapter 41, quantum oscillator? Okay, and this f, the frequency, is determined by the effective spring constant, K effective between these two atoms, as well as the reduced mass mu, m1, m2 over m1 plus m2. Okay, that's from physics 1b. So, and that's from 1d, from the quantum oscillator calculation. And therefore, when we plot the energy diagram, we are going to get this. The energy gap is a constant. It's h times f. I told you before, when we discussed quantum oscillator, the simple harmonic potential or parabolic potential is the only potential whose solution will give you an evenly spaced energy diagram. So when you see an evenly spaced energy diagram, tell yourself this is a simple harmonic potential. Indeed, that's the case here. Okay, so what is the photon energy released as the system jumps from this level down to the next level? The energy released in terms of photon, right? Energy of the photon equals delta E vibrational from here to there, and energy gap is hf. F here is the frequency of the photon, but delta E vibration is also equal to h times f of the vibration, the frequency of the vibration. So therefore, the frequency of the vibration equals the frequency of the photon emitted. Okay, so again, you have a vibrator made of two atoms like this, and the vibration has a certain frequency called f vibe. As a result, if the system makes a transition in energy from one vibrational level to the next vibrational level, the emitted photon will have the same frequency as the frequency of the vibration of the two-particle system. Now, what's the typical value of the vibrational frequency? Well, the typical value is 10 to the 13 hertz, it turns out. That depends on how close the molecules, the atoms are, and how strong is their interacting potential energy, which means what is the effective K value, the spring constant value. It turns out that's a typical value, 10 to the 13 hertz. This is 2 orders of magnitude higher than that of the rotational frequency, 2 orders of magnitude higher. Okay. And we put this in the IR, infrared range. This is not visible light, which is 10 to the 14 hertz, but this is IR, infrared. And how significant is this energy gap compared with the energy itself? Do we have to consider the energy, the energy quantization? Well, let's do that. Let's estimate delta E, the energy gap, divided by E itself. And that equals to HF, that's the energy gap, divided by V plus 1/2 HF. V is the quantum number, 0, 1, 2, 3, and so on. And, if V is not a very large number, usually it is not, then this ratio is not very small. It's of the same order of magnitude as 1, and therefore, just like the rotational case, the vibrational energy spectrum is very much quantized. You cannot ignore the quantization between neighboring levels. Okay, we have studied all three modes of energy: kinetic energy for translational motion, kinetic energy vibration, and the total energy of vibrational motion. Now, let us compare these three cases in terms of their quantization, and also let's compare the typical energies associated with these three modes of motion with the ever so important value of kT, which is the average kinetic energy possessed by an average particle at room temperature, T being about 300 Kelvin. Again, at T equal to 300 Kelvin, kT is about 1 over 40 eV. K is the Boltzmann constant. What is the meaning of kT again? Well, if you recall from physics 1b, if you look at the air molecules in this room, some air molecules will have greater kinetic energy, some will have less kinetic energy, but on average, the kinetic energy possessed by each air molecule is of the order of kT, of the order of kT. Okay, the translational part is actually 3 over 2 kT, but the order is kT, which means as the molecules go back and forth, they hit each other, they bounce back, whatever, the energy possessed by each one, the kinetic energies, is about 1/40 eV. And the kinetic energy for translation is quantized, but the quantization, the energy gap, is of the order of 10 to the negative 21 eV, which is no match for that. So the energy for the translational motion is far greater than the quantization energy gap. Therefore, we say no quantization necessary. It is just thought of as a continuous spectrum. Okay, continuous spectrum. It can possess any energy for translation motion as far as we're concerned. No quantization. But the rotational part is more interesting. First of all, the rotational part of the energy itself is of the order of 10 to the negative 3 eV, which is about the same as the energy gap between one rotational energy and its next neighbor. So we're talking about a pretty good amount of discreteness or quantization. The energy gap is no longer much less than energy itself. It's comparable with the energy. And this delta E is about 1/10 of kT. kT is 1/40 eV. Okay, so what does that mean? It means that even though there's an energy gap, an average molecule will have roughly 10 times the energy of this energy gap when they hit another molecule. That means an average molecule in a typical collision at room temperature will have enough energy to move the quantum state of itself or another molecule from one level of the rotational energy to another level, because it can jump a few steps, in fact, because it's got 10 times, right? The kT is about 10 times this energy gap. So therefore, in a typical collision at room temperature involving two air molecules, there can be change in the rotational energy level. Okay, the molecule can go from this level to that level, go from this level to that level, and so on. This all happens, and energy typically associated with energy transition from one level to the next is the microwave range. And the vibrational energy is a different story. The energy gap is of the order of 10 kT. All right, 10 to the 14 hertz, that's the frequency. 10 to the negative 1 eV here is about 10 to the negative 2 eV, and therefore the energy gap is about 10 times kT, or 10 times the kinetic energy of average molecule colliding with another molecule at room temperature. So in a typical collision involving two air molecules at room temperature, you cannot expect one of them to jump from this level to the next level, because there's just too much energy at too much energy required. Okay, you cannot have 10 times the typical energy to go from here to there. You just don't have that much energy. So therefore, in a typical collision, the vibrational energy stays the same. It doesn't make a transition from here to there. There is simply not enough energy to do that. So therefore, the vibrational energy levels are thought as frozen. They do not contribute to the specific heat at room temperature. We saw that in physics 1b as an experimental fact. Now we have some theoretical argument why that's the case. Okay. The rotational energy level is still okay because energy, even though it's quantized, energy gap is narrow enough, is small enough so that I can use kT to overcome it. And translational, we just don't worry about any energy quantization. So we should include rotation and translation, but we should not include vibration when we calculate the specific heat. And that agrees with what we learned in physics 1b. Finally, let us combine the rotation and vibrational energy of a molecule, and let's see if we combine both of these energies, then what kind of frequencies, what kind of light can come out of this molecule as the molecule makes a transition from one initial state to one final state, which can result in a change of both its rotational and its vibrational states. So we add the vibrational energy and rotational energy up. Okay, this is the vibrational part of the energy, quantum number V. Here is the rotational part of the energy, quantum number J. We don't worry about the translational part because it's not quantized at all, so there's no discrete spectral line coming out of it. Now, we said that this has the order of 10 to the negative 3 eV. This one has the order of 10 to the negative 1 eV. So we're talking about 100-fold difference. This is about 100 times as great as that. So as you change J, this thing is not going to change by much compared with that. But when you change V, we're talking about a huge change. And therefore, within the same V value, we can vary J. We can have a whole bunch of different J's. And we go to a different V, we get a whole bunch of different J's. Okay, but there is a significant gap between different V values of the, different V values. Bunch of J's with the same V, bunch of J's with the same V, but there is a big gap. Okay, because of this factor here. It turns out that as a molecule makes a transition between one of these states to another one of those states, it cannot jump arbitrarily from an initial state to a final state. There is a restriction for the quantum number J, which is the quantum number for the rotational angular momentum. It turns out that J can only change by either positive 1 or negative 1. Delta J is plus or minus 1. You wonder why that's the case. In fact, the reason why that's the case is very simple. It's the same rule, delta L, for an electronic transfer from one state to another within the same atom. Delta L has to be equal to plus or minus 1. Same idea. Because as this photon moves away, it carries some kinetic, angular momentum. The photon is a spin 1 particle, okay? So it has an angular momentum of h bar. Where does the angular momentum come from? It comes from the angular momentum of the molecule. And the molecule starts with a quantum number J for its rotation. J must change by 1 unit so that the change in angular momentum of the molecule is also h bar, 1 unit of h bar. That is a matter of conservation of angular momentum. So delta J must be equal to plus or minus 1. If you see delta J equal to plus or minus 2, what does that tell you? 2 photons must have escaped as a result. And that is a very rare event. And therefore, we usually don't discuss that. Okay, so that's conservation of angular momentum. Now, delta V can be anything really, but we usually discuss the case only from one V to the next neighbor. If you go to another one, the energy difference will be even greater. We usually don't discuss that. Okay, so let's consider V to V plus 1, so that a light comes in, that light gets absorbed by the molecule makes a transition from a low energy to a high energy state. So that's absorption spectrum. You can also go back down, that's the emission spectrum, it's symmetrical. All right, so let's consider the case when V becomes V plus 1, and delta J is either positive 1 or negative 1. Using this formula, with delta V equal to 1, and delta J equal to positive 1 or negative 1, you will arrive at these two possible results. The energy of the photon, either this one or that one, depending on whether delta J is positive 1 or delta J is negative 1. For example, if delta J is positive 1, okay, we have to look at this. We have to look at this result. This is when you go from J to J plus 1. J to J plus 1. And then here, this is our first possibility, j to j plus 1. So you have j equal to 0 to j equal to 1. Here you have j equal to 1 to j equal to 2. Here you have j equal to 2 to j equal to 3, and from 3 to 4. All of these belong to the same subcategory of delta j equal to 1. All right? Here's a positive sign. Now, if the final result is delta j equal to -1, you have to use this equation. This happens when you go from j equal to 1 to 0. Okay, here is 1 to 0, or 2 to 1, or 3 to 2, or 4 to 3, and so on. Now you notice you cannot go from 0 to -1 because there's no such thing as j equal to -1. Okay, so this guy, you can only go from 0 to 1, but you cannot go from 0 to -1 because -1 never existed. So these are the possible values of j's. Okay, now you take a look at these equations. You find that the separation between nearest neighbor frequencies is even. The frequency of this line, this line, this line, this line, the separation is the same. The separation, you look at these guys, they all have the same delta j, okay? So delta j equals +1 for all of these guys. And the frequency difference is also a constant, h bar over 2 pi I. You can get that by taking the delta E, this delta E, and all you have to do is divide it by h, then you get f. Okay, you get f. And you find, it's even spacing. J equal to 0, 1, 2, 3, and so on. Here j equal to 1, 2, 3, and so on. But you notice that this middle line is missing. This middle line would be j equal to 0 to -1, but that doesn't happen. Okay, if you go with j equal to 0 to -1, then you can plug in 0 here, you get hf, which is right in the middle. Again, that doesn't exist because j equal to -1, the final destination, is not real. So therefore, this line is missing. But here you have a center line that's missing, and everything to the left and everything to the right are totally symmetrical with even spacing. So it's a nice diagram, spectrum diagram, if we actually plot it. Here is our example. HCl. This is the absorption spectrum of HCl. This is the one in the middle, missing. HF, that's missing. And everything here, all these lines correspond to delta L, delta J equal to +1. All of these, delta L, delta J equal to -1. You see the nice even spacing here? Another thing I want to talk about is that there is an overall profile for the intensity. The intensity is pretty weak, and it becomes stronger, 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 and it becomes weak, 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 and it's symmetrical. First of all, it's symmetrical. That makes total sense. Okay, that makes total sense because we're talking about the same kind of energy, essentially the same kind of energy transition. That makes sense. But why this profile? Why does it start from very small and go up and then go down like this? Why is that? The idea is very simple. The intensity of the absorption line depends on how many times this kind of transition takes place, right? This kind of absorption of light takes place. If a lot of them take place, the intensity is high. And that transition is from this state to that state, initial state to final state. If I have a whole bunch of molecules in that initial state, then a lot of them can make that transition and the intensity will be high. So you see, the intensity pattern depends on the number of photons absorbed, which in turn depends on the number of molecules being in this initial state, which is proportional to the probability of finding this molecule to be in this initial state, right? Now remember, all of these molecules, they have the same V value to begin with. Everything goes from V to V plus 1 upon absorption of that photon. So V is the same for all of these guys. Okay, so V doesn't matter. What matters is J. J changes between different states, between different initial states. Here, these states are different only in J values. V is the same. See that? Okay. So when you change J, how does that change the energy of the system? The energy of the system depends on J in this manner. H bar squared over 2I times J plus 1, right? The J part of the energy is like this. And the probability of finding a particle or molecule to be in this state depends on the energy of that state. This is the energy of the state. There's the Boltzmann factor, e to the negative energy over kT. That's the probability, relative probability, the Boltzmann factor. So you have e to the negative h bar squared times j plus 1 over 2I. So that's that factor here. That's part of that profile. Another part of the profile is that given a state j, okay, given this state j here, say j equal to 2 here, for example, how many different possibilities are there within j equal to 2? Well, there are 5 different values for j equal to 2. That is the z component of the angular momentum, which is characterized by mj, okay, by the quantum number mj, can go from negative 2 to positive 2. In fact, it's negative 2, negative 1, 0, positive 1, positive 2. There are 5 different values, right? In general, there are 2j plus 1 different values for mj, corresponding to the same j. So all these are the same energy j, same quantum number j, but there are different substates for that. The more states there are, the more particles you can find there, because there are more states available for them. Okay, so the envelope, which represents the intensity, should be the product of this 2j plus 1 and the Boltzmann factor. As you go to higher and higher j value, there are more states available because mj has more variation. That tends to increase the chance of finding a particle there because there's simply more states available. But on the other hand, you also have the Boltzmann factor, which decreases as the energy increases. So you have an increasing function times a decreasing function. As a result, you have it's going to go up first and it's going to go down. That's exactly what this profile stands for. You can in fact fit this profile to this function and you get a very good match. So in this lecture, we took a quick look at molecular bonding mechanism and the corresponding energy spectrum of molecular motion. In the next lecture, we're going to go beyond a single molecule. We're going to look at how molecules can form solids by bonding together. And that is the subject of the next lecture, bonding in solids.